Okay. Good evening, everyone. Thank you so much for coming to our October public talk. My name is Hannah. I'm a graduate student here at the Trottier Space Institute, and I'm also the TSI outreach coordinator. So I'll be your moderator for tonight. So tonight, the public lectures by our three panelists will be all about eclipses, because this month, as well as in a few months, Montreal will experience a few solar eclipses. So just to give a small hint at what that will be like, maybe I should turn off the lights. So in 2024, Montreal will experience a total solar eclipse. So this path here is the path of total darkness for the upcoming solar eclipse. And if we look at ourselves over here, we might think that we will just miss it. But if we zoom in all the way in, you will see that the southern tip of Montreal will experience total darkness in April. So that's why we're so excited to bring you all here tonight and talk about why this is going to be so great. And to do that, we have three wonderful experts who I will introduce in a moment, who will teach us all about this phenomenon here on Earth, as well as elsewhere in the universe. Just as a quick advertisement, we have two public talks coming up for the rest of the semester. The first one, which is in November, will be a recap of the science that went into this year's Nobel Prize in physics. And then we will also have one about pulsars in December. So get excited for that. Just very quickly, I'll flash our code of conduct. So just a reminder that the Trottier Space Institute is committed to providing science education to everyone in our community in a way that's positive and making sure that everyone has a great time. So I'll just leave this here for a moment for everybody to read. And at any point in the event, if you have any questions, scientific or otherwise, you can reach out to one of the volunteers that you saw when you came in, or myself, or you can email us at tsioutreach@physics.mcgill.ca. Also, don't forget that you can win a mug, our very new TSI mug. So make sure you scan the QR code. And last but not least, it's my pleasure to introduce tonight's speakers. First off, we have Guillaume Poulin, who's a science communicator at the Mont-Mégantic Astro Lab, and who came all the way from Mont-Mégantic to speak with us tonight. So thank you so much for joining us. We also have Dr. Heidi White, who's the science outreach officer at the Trottier Institute for Research on Exoplanets at the University of Montreal. And finally, we have TSI graduate student Matthew Lundy, who some of you might know from our wonderful observing nights, because he runs the Anna McPherson Observatory, which is on the roof of the Rutherford Physics Building. So with that, I would love to invite Guillaume to give the first short lecture. So that will be. No, that's Matt's.
Good evening, everyone. First of all, I'd like to start by saying that I'm not really used to talk in English in front of large crowds. Usually people who come to Mont-Mégantic speak French, so excuse me if I'm not necessarily very fluent. But as you all know, as Hannah said, there's a few eclipses coming. The big one is on April 8th. Yeah, usually that should move. Anyway. April 8, 2024. And so that everyone can be ready for this eclipse, I'm going to start by doing a short course on eclipses. So eclipses 101. What is an eclipse? First of all, the meaning of the word eclipse comes from the Greek, and it means disappearing. So it's something passing in front of something else, usually planets, moons, stars. And in the solar system, we have a few examples where eclipses can occur or not. For example, there's a part of the screen that's missing. Anyway, the two innermost planets don't have moons, so if you were to stand on these planets, you would not experience eclipses. But from the Earth, we can have sort of eclipses with these two planets. We call these transits because from time to time, they can pass in front of the sun. For example, a few years ago, Mercury, the small black dot that you see in the lower part of the image, passed in front of our sun. And in June 2012, we had the Venus transit, which is even more rare. I don't know if some people here have seen this transit. Yes, one person. If you missed it, the next one is like in 100 years. So sorry, too bad. If you would go to Mars, in fact, we've seen eclipses on Mars. No humans, but robots have seen eclipses. For example, this is the Perseverance robot. And I'm really sad because I have like lots of videos and they do not seem to work. But we could see Phobos, one of Mars's two moons, passing in front of the sun. And the giant planets, Jupiter, Saturn, have so many moons that eclipses happen all the time there. For example, a few years ago, there was a triple eclipse that was observed on Jupiter. Jupiter is very interesting because it has almost no tilt relative to the sun. I think it's like 3 degrees. So the plane of the moon, the sun, and the planet Jupiter will align much more often than it does, for example, with Saturn, which has 145 moons. Depending on what's your definition of moon, because some small rocks are considered to be moons on Saturn. And what I find is interesting is that for close to 15 years, there was a probe in orbit around Saturn, the Cassini space probe. And from Cassini's point of view, eclipses happened all the time with Saturn. For example, we could see moons eclipsing the planet. We could see moons eclipsing other moons. We could see the rings eclipsing the moons. We could see moons eclipsing the rings. You get the gist of it. The rings eclipsing the planet eclipsing the ring. And if Cassini was in the right spot, which it did on some occasions, like in 2013, you could see Cassini could see a solar eclipse, but with Saturn in front of the sun. So this is a true picture. It's one of my favorite pictures of all time. So the sun is behind. You can see light not reflecting in the eyes of the rings, but more diffused by the rings. And one other thing I really like about these pictures is that if you look carefully, there's a small dot right there. This isn't the moon. Well, there's a moon there, ours and our planet as well. So I don't know if you remember where you were on July 19, 2013, but you were there. I can tell you that for sure. If we come back to the Earth, when we have alignments between the Earth, the moon, and the sun, we have eclipses. And if we look at that from a view north of the Earth, we would be tempted to think that every month there's such an alignment. The moon passing in front of the sun, and the sun passing, the moon passing in the Earth's shadow. But that's not the case because the two planes, the Earth and the sun plane, is still, okay, I will just start over. The moon's plane around the Earth is tilted relative to the sun-Earth plane, about 5 degrees. And it's only when those two planes align that we can have an eclipse. This is called an eclipse season. It lasts for roughly 6 months. It happens every 6 months and like 173 days. So we have an eclipse coming in just about a week from now. So we are one eclipse season away from the 2024 total solar eclipse. So yeah, there's no eclipses. There's not an eclipse at every moon cycle. Yeah. So first of all, lunar eclipses. These happens at night, and they happen when the moon passes in the Earth's shadow. If it just flirts with the shadow, we can have a penumbral eclipse or a partial eclipse. But if it passes straight into the Earth's shadow, then we have a total lunar eclipse. Sorry. So the Earth's shadow is quite large, so the moon can spend almost an hour inside the Earth's shadow. So that's the total phase, and the partial phase will last even longer. Has anyone here seen such an eclipse in their lifetime? Yeah. You probably noticed something very weird, is that even though the moon is in the Earth's shadow, it doesn't disappear completely. Why is that? Well, if you were to be on the moon during such an eclipse, this is pretty much what you would see. You would see a ring of light, a red ring of light around the Earth, which is basically the light from all the sunsets and all the sunrises of the Earth at the same time. So there's a tiny bit of light that is diffused that makes the atmosphere blue, but a tiny part of it passes through the atmosphere, is diffused, and it's only the red light that reaches our moon and gives it that red color, which is sometimes called the blood moon, which is something I really don't like, just like supermoons, sorry. So yeah, I saw a lot of hand risen when I asked if you saw a total eclipse. Total lunar eclipse happen every year, and they usually most people have seen one, and the reason for that is that they are pretty easy to see. They are not dangerous because you're not looking at the sun, but also it's always a whole hemisphere of the Earth that can see the eclipse, which is not the case with solar eclipses. Solar eclipses happen about at the same rate as lunar eclipses. They happen, of course, during the day when the moon passes in front of the sun, but you really need to be at the right place at the right time to see a solar eclipse. So the moon throws a shadow on the Earth, and there's two parts to that shadow. There's the umbra, where the sun is totally black, and the penumbra, where it's partially black. So if you were to stand in the penumbra, what you would see is a partial solar eclipse, which is what we will see next week here in Montreal, in southern Quebec. This is a picture I took in Mont-Mégantic a few years back in 2021, I think. You can see the Mont-Mégantic Observatory right there next to the sun. An interesting thing about these solar eclipses is that the moon, as you might know, doesn't revolve around the Earth on a perfect circle. It's an ellipse. So the moon can be further on its path when it covers the sun. And if it happens at its farthest point, then the moon will not throw only a shadow, but what we call an antumbra. So if you were to stand there, what would you see? Anyone knows? In the antumbra? You would see the moon smaller than the sun's diameter, and there would still be a ring of light passing. This is called the annular solar eclipse. And so next week, eclipse that we will see as a partial eclipse here is going to be an annular eclipse in some parts of the United States. So if you know people living on the West Coast, if you want to travel, the blue path that you have there, this is where you need to stand next week if you want to see the annular solar eclipse. So if you stand in the penumbra, you have a partial eclipse. If you stand in the anteumbra, you have an annular eclipse. And if you stand in the umbra, then you have the best of the best, the most gorgeous eclipse that you can have, which is a total solar eclipse. So you stand in the path of totality. And like I said earlier, you really need to be at the right place at the right time to see such an eclipse, because the moon's shadow travels very, very fast on the Earth's surface. I was surprised researching for this presentation that it's about 4,000 kilometers per hour, the speed at which the shadow passes. So total solar eclipses are not more rare than other types of eclipses. As you can see, they represent close to 27% of all the solar eclipses that we can have. It's just that in order to see such an eclipse, you really need to be in that tiny region that we call the path of totality. So a few years back, there was an eclipse, another one in the United States, another total solar eclipse. And this is the tiny line. It's about 150 kilometers wide. And this is where the moon's shadow passes on the Earth. And this path of totality will come to southern Quebec in just 6 months from now. But I'm curious to know, has anyone here ever seen a solar total eclipse? Yes. Oh, yeah. Where? When?
Oregon.
Oregon. Okay, so 2017. Yeah. The others? Of course. Yes. And? 2006? Yes. Yes. Good. So some people travel to see such eclipses. It's very rare. And what's so like it's very rare to have one coming to your area. In fact, an eclipse will happen twice at the same spot, on average, once every 350 years. So it's very rare. In fact, there's probably the worst place on Earth is Regina in Saskatchewan, and not because it's Regina, but because the last time they had a solar eclipse was close to 2,000 years ago. But as you will see, Quebec was pretty lucky in the last century, and the last total solar eclipse we had here in Quebec was in 1972, July 10th. So it passed on Captcha. There was like a few thousand people there for this eclipse. That's probably the most people they ever saw in their life. But unfortunately, it was very cloudy. So only a few people saw the few minutes of totality there. Before that, July 20th, 1963. So it goes back quite a long way. I don't know if some people have seen this eclipse here. No. As you can see, it passed over Trois-Rivières, Victoriaville, and Mont-Mégantic was in the path of totality. At that time, we had 24 seconds of totality because we were on the edge. And the last eclipse to pass on the city of Montreal was in 1932. So that's quite a long time ago. And once again, Mont-Mégantic was in the path of totality, 34 seconds this time, so a bit better. But coming next spring, we'll be even more lucky in southern Quebec because this is where this eclipse will be visible. Drum roll. So Sherbrooke, Montreal. If you were here at McGill during the eclipse, you would have about 1 minute and 20 seconds of totality, which is quite amazing. But the best place to be during such an eclipse is, of course, where the sky is clear. Let's be clear about that. But it's at the center of the path of totality, because as you go closer to that centrality line, the eclipse lasts longer. So Montreal, 1 minute, 20 seconds. If you go to Saint-Jean-sur-Richelieu, it's about 2.5 minutes. And if you go on the centrality line, 3.5 minutes of totality. And as you might see, there's a place called Mont-Mégantic, which sits right on the path of totality. So halfway between the Astrolabe, where I work, and the Mont-Mégantic Observatory, this is where the eclipse will be at its best. So of course, you might have guessed we'll have a big event there. We expect to have a few thousand people coming in early April, which is a big challenge because of all the snow we have still at that period in Mont-Mégantic. But we also will be live streaming from the mountain if you want to catch that. So in the end, why are these eclipses so special? Why are total solar eclipses so special? There's an incredible cosmic coincidence. that makes the moon and the sun pretty much the same size in the sky. The moon is 400 times smaller, but it's 400 times closer to from the sun. So they have roughly the same angular size, which means that when the moon does pass in front of the sun, unless it's an annular eclipse, then the moon will barely cover the sun's disk, which allows us to see all the gorgeous details of the corona, some solar flares as well. So nowhere else in the solar system do we have that perfect ratio where a moon will have the same size as the sun. So our solar eclipses are very, very special here on Earth. But also, there's something else that makes these eclipses very special, is that here there's people who can watch it, who can be moved by such a spectacle. I've been very moved by the first time I saw an eclipse. To be totally honest, I cried during the totality because it was really so overwhelming. So if you've never seen a solar eclipse, I really urge you to do everything in your power to be somewhere in the path of totality, either in 2024 or maybe in 2079, when the next total solar eclipse will happen in a tiny part of Quebec. If you miss that one, well, 2106 is your next chance. So on that, I'll leave it to Heidi. Thank you. Have a good night.
Okay, so hello everyone. My name is Heidi White, and I am an astronomer at the Trottier Institute for Research on Exoplanets at the University of Montreal. And I'm going to be talking today about alien eclipses. We just learned about, thank you, Guillaume, for your amazing introduction to eclipses. We just learned about all the eclipses that can happen inside our own solar system. I'm going to extend that a bit to talk about eclipses that happen involving alien worlds. So when I say alien worlds, I mean exoplanets. Does anybody know what an exoplanet is? I'm going to put the definition up. So yeah. Most people are familiar with the idea of exoplanets. So these are, it's a term that's short for extrasolar planet, and they are planets that orbit stars other than the sun. So they are planets within other planetary systems. And over the past 30 years, we've discovered thousands of these systems. We have to date about 10,000 candidates for alien worlds, and over 5,000 of those have been confirmed. And if there's one takeaway you want to know about exoplanets, it's that exoplanets are common. Planets in our galaxy are common. In fact, they're so common that we think that there's about, on average, one planet orbiting every star. So within our own Milky Way galaxy, remember that's just one of potentially trillions of galaxies in the observable universe. We're talking hundreds of billions of planets. So yeah, exoplanets are pretty cool. So how do we find these exoplanets? Interestingly enough, we often find them by eclipses. So as Guillaume just introduced, a solar eclipse occurs when the moon passes between the sun and the earth, and that casts the moon's shadow on the earth. So this same phenomena, something moving in between our line of sight and blocking the light from a bright object, this can be extended beyond our own solar system into the realms of other stars. And so while there's a handful of ways in which we can find exoplanets, discover them, the most successful method to date has been using exoplanet eclipses. So how do these exoplanet eclipses work? So to understand how they work, let's start with a little diagram. So on the left, this is depicting what we see typically when we observe exoplanets. So our telescopes point at stars, and when we look at an exoplanetary system, we see them as like a fuzzy point of light. But this light that we see from the system is actually the combined light of everything within the system. So the star and all the planets. So let's just consider a basic system of just one planet and one star. And that's what we see on the right. So the brightness of the spot, it includes the combined light from the star and that planet. So the light we see is the star light and the planet light. So some fraction of these exoplanetary systems will be oriented in such a way that there are interesting opportunities for eclipses to happen. You can imagine, imagine we're observing, looks a little close, this is not the scale, we're observing an exoplanet system, and we're monitoring the brightness from that point in space. And if it's oriented properly, we're looking along the plane of the orbit of the planet, then there will be multiple opportunities where the planet will pass behind the star and pass in front of the star. These are the opportunities that I'm referencing. So when an exoplanet passes in front of its star, it will block some of that star's light, right? And so for a short time, the star's brightness will appear to decrease. And in fact, the overall brightness we see from this system, because it is dominated by the starlight, will decrease. So another word for this type of eclipse, technical term is a primary eclipse. We often reference this as a transit. And so this is when the planet passes in between us and the star. So if astronomers detect that a star's brightness decreases and then increases again, they can deduce that possibly there's a planet orbiting that star. This is precisely how we found most of our exoplanets. There's also something called a secondary eclipse. So when a transiting planet disappears behind the star, as seen from our line of sight, the total brightness of the system also decreases a tiny bit because the planet's light is being blocked. So in both cases, these eclipses can result in little decreases, or as we'll see in a second, dips in the amount of light received by our telescopes. Let's see if this movie plays. So this is going to illustrate how we get that dip. So here you have the planet orbiting the star. And you can see on the vertical axis, that's the brightness, how bright does something appear to us? And then you have the time in hours on the horizontal axis. And so as it swings around, when it passes, the planet passes in between us and the star, you can see it blocks some of that light, and that's that dip that I'm referencing. Okay. So what I want to emphasize here is that this is a very tiny dip in light. So here we have a graph, it's a little cut off there, but the label on the vertical axis says the observed star brightness. So it's just like we saw before. And then time on the horizontal axis. So basically same values. And you can see as the planet passes in front of, that's referencing that little dip that we see there. But the star's brightness, when it's detected in our telescopes, that light collected by our telescopes, it's only going to drop by a tiny fraction, about 1% to 1/100%. And so this is very tiny. You need very sensitive detectors and really clean data to be able to see these dips in light. Now, if I just see one of these dips, would that make you confident that we have indeed detected an exoplanet? What might be another thing we look for in the data to feel confident that this is a good candidate? Natural fluctuations in the light of the star can definitely cause dips like that. Yeah, over there.
Some sort of frequency to observe the dips.
Why might you expect to see the dips, like more than one dip?
Well, because the planet revolves around the star.
Exactly. Yeah. So the planet is constantly moving around that star, which means we should expect to see dips with some periodicity, some frequency, right? So yeah. So a light curve actually has multiple dips in it. We're just showing one. So again, this is a very tiny dip in light. So for a Jupiter-sized exoplanet, this is like sensing the drop in brightness of a car's headlight when a ladybug flies in front of it. For a Jupiter, think how big Jupiter is. It's the biggest planet in our solar system. And that's what we're seeing, we're detecting with our telescopes. For an Earth-sized exoplanet, this is a bit like watching maybe a fruit fly pass in front of a headlight. This is really tough work, but regardless, we are finding tons of systems, tons of planets, and so it is a very successful method. Planet transits, exoplanet eclipses can also help us characterize these planets that we've been finding. So during a transit, some of the star's light, it is blocked, but some of it will travel through the planet's atmosphere if that planet, that exoplanet, has an atmosphere. And as that light from the star passes through the atmosphere of that exoplanet, it gets sort of filtered. And when this happens, some of the light from the star, certain colors, you can see here that you can see light passing through the atmosphere and it's entering, like a bit of a prism, right? Prisms can break up white light into its colors, into the different colors. And so that's sort of what we're illustrating here. And when this filtering happens, some of the light, certain colors, parts of the light, the spectrum, get absorbed. And the surviving light, it contains less of certain colors as a consequence. And that's shown here as these dark bands. Now, this process of filtering creates an imprint on the planet's atmosphere, or an imprint of the planet's atmosphere on the light we see from that star. And because each atmosphere is composed of different molecules and different species, each atmosphere will create its own unique imprint. And so here in this illustration, we have light entering, it's the star in the up left, and it's passing through that atmosphere with all those molecules. It's a very thick atmosphere with molecules and stuff in it. And those molecules and the stuff in there, those species are absorbing certain colors. And so when we break it up, we see some missing, right? Now, I have to take a moment to talk about NIRISS. So NIRISS is the Near Infrared Imager and Slitless Spectrograph, and is one of the 2 Canadian contributions to the James Webb Space Telescope. And NIRISS is designed to help astronomers find exoplanets and study those atmospheres. So their search in this process, remember, characterizing atmospheres is incredibly important for the search for life in the solar system, or I'm sorry, the search for life beyond our solar system. And so what happens is we can detect these exoplanets, we gather images of distant solar systems, and then the NIRISS will, as they pass, these transits happen, these eclipses, it will gather the spectrum of light that filters through that atmosphere, and then we will analyze it to determine of exoplanets' potential for life by looking for what kinds of light is missing and what does that say about what that atmosphere is composed of. So this process of examining light that's filtered through the atmospheres of exoplanets to explore their composition is what's known as transmission spectroscopy. And this Canadian instrument aboard the Webb Space Telescope has already allowed us to make some really amazing discoveries using this method, this transmission spectroscopy, including helping characterize recently the atmosphere of K2-18b, cut off there. And so K2-18b is a possible ocean world. It's not a type of planet we have in our own solar system, but that's actually quite common. If we look at the types of exoplanets we find, ones we most often find are not ones that we find within our own solar system, which is interesting. And this possible ocean world is within the habitable zone of its stars. So that's that region where there's a potential for life like us, right? Liquid water could exist on the surface of that planet. And also detected a possible biosignature, dimethyl sulfide. So biosignatures are features in the spectra that can be used as evidence for past or present life on that exoplanet. And so it's not a conclusive sign of life, but it is one of the things that we look for when we're looking for evidence of past and present life. And so it's really, really interesting, very, very cool. So I hope that I've been able to highlight here all the different things the cool things that we can learn about exoplanets, both their detection and understanding more about what they're composed of, what kind of worlds exist out there in the universe, using this very same principle of eclipses via transits. Now, before I wrap up here, I just want to do a plug for an event. So Saturday, October 14th, as Guillaume mentioned, we're going to have a partial eclipse in Montreal. And at Université de Montréal, we're going to be having an event at our campus mill. It's called Astro Mill. And we will be it'll be running from 11 a.m. to 4 p.m. on our campus. We're going to be having bilingual activities, so English and French everywhere for all ages. And it is a unique experience unique opportunity to experience a partial solar eclipse and learn more about what you can do to watch the great eclipse of 2024 from Montreal. So at our event, we're going to be handing out free eclipse glasses. There they are. Great. So I have one pair here. So if you attend our event on October 14th, you'll be picking up a pair of these eclipse glasses. Hopefully, we'll be watching a partial solar eclipse. We'll be doing the solar observing. We'll be having cosmic face painting. We'll have 7 demo booths where you can learn about all different aspects of eclipses, including our new booth titled Sensory Astronomy, where you can actually explore astronomical data, not just using your eyes, but using touch and sound. You can build your own eclipse viewer for April 2024. There'll be live streams of the eclipse, including streams from Mont Mégantic. We'll have a photo booth, tons of stuff. Anyway, this is my plug. Please come out on October 14th to our event. I promise you, you will have an amazing time. Thank you.
Okay, so hello everyone. Today I thought I would use kind of eclipses as a bit of a chance to discuss the process of actually doing science. And so I'm a graduate student here at McGill, and I participate actively in research as a part of a large kind of international collaboration called Veritas. And part of the work that I do is studying things very, very similar to eclipses that we call occultations. And I'll talk about that, but I just want to talk about the process of eclipses kind of generally in the past, what they've been used for, and kind of how really kind of the science that we're doing today and the science that was being done hundreds of years ago is a process of repeated and kind of continuous mistakes, which perhaps is not what you were expecting, but this is what I think is really interesting about these things. So our story kind of starts back in 1911 with somebody that you perhaps recognize. This is the star of a recent blockbuster film, Oppenheimer, but this is Albert Einstein. And one of the things that Albert there was quite famous for uncovering, but not what he actually won the Nobel Prize for, was this idea of general relativity. The idea that the fabric of space-time, the bending of the fabric of space-time, is what is actually creating the illusion of this kind of effective gravity that we thought was a force. And that has some really interesting implications and things that you can directly observe. And one of those things that you can directly observe is the bending of light around large gravitational objects. And one of those we have conveniently within our own solar system, which is the sun. And so if you were to kind of want to test this idea that this crazy physicist had, what you'd need to do is look around the sun and see if you could figure out that light from the apparent positions of stars was changing as the sun passes in front of them. A really, really kind of simple thing to do, or kind of so you would think. But measuring stars right next to the sun is quite difficult. for kind of one very simple reason. The sun is incredibly bright. And so if you were to try and measure some stars during the day, it becomes incredibly difficult. So you need a unique event where the sun will disappear for a convenient amount of time for you to take your photographs of these bending starlight, and then you can see whether or not this kind of test of what we call general relativity is correct. And the eclipses provide this kind of perfect opportunity. But like everyone was mentioning, if you just sit around, you could, but you have to wait something like kind of 300 years to do it within your city. And that is because, again, this moon shadow, so this is from actual satellite photos, weather satellite photos, and you can see that moon shadow passing kind of across the Americas there at the top. And you can see that the actual part, that really dark patch in the middle, that umbra that was talked about earlier, is only covering a very narrow region. And so if you want to see this thing, you're going to need to travel. And so past 1911 and around 1914, there was this group that was organizing this trip, and it was an international group as well. So they were coming from, we had kind of Irwin Finley from the Berlin Observatory. We had kind of William Wallace Campbell from Lick Observatory down in California. And then we had Charles D. Bren at the Argentinian National Observatory. And so you assemble this kind of crack team of some of the best observational astronomers at the time. We're all interested in confirming this theory. They all fly to the Black Sea where they can predict this eclipse. And if this was kind of a movie, that would be the end of the story. But this is not what happened, because if you really caught the kind of year that I was talking about, this was on August 21st, 1914. And those who are more familiar with history than science might recognize that that is right around the start of World War I. And so you can see kind of a note from one of their papers. Most unfortunately, the outbreak of the war compelled him to interrupt his preparations and to abandon the instruments. So I think you can forgive them for that. Quite a few of them ended up becoming prisoners of war, and some were sent home back to Germany. And so this initial attempt with the people who were left over from kind of Argentina and the US actually also couldn't observe the eclipse because of clouds. So kind of a next group was organized in about 1918 in the US, and this one also failed, once again because of clouds. So you can see here a quote from them. The only permanent observatory along the line of totality, so kind of the equivalent of where Montmégantic would be for this eclipse, was kind of suffered from the most clouds. And so this picture from that eclipse was taken from Wyoming with a group that was described as having a powerful automobile, which was quite impressive at the time, apparently. So now, kind of a quite tropical tour is our next eclipse that we're going to, and this one is the eclipse of kind of 1919, and at this time, the person who we're looking at is actually Arthur Eddington, who is known for quite a few other kind of discoveries within physics, but at this time, he was just in his mid-30s, and he was actually also getting drafted into the war, and he received an exemption from that draft to do this eclipse observation. Wouldn't that be nice for all of us? And he traveled down to where just that line there is, just off of the coast of Africa, down in kind of Principe there, off right there. And there was also observations happening simultaneously off the coast of Brazil. And here are some of those observations. And this is actually the first kind of observational evidence. Those little kind of star spots that you see, some of these are noise, but just around that kind of third image are what actually is the kind of first evidence that we have of general relativity. But this was a process that didn't happen instantaneously, kind of from the initial theories and predictions in 1911. It wasn't until kind of 8 years later that we were able to actually get the kind of observational evidence and proof of this thing. And that still really happens today. You can come up with the best idea that you want, and sometimes nature and the universe just refuse to cooperate with you. And that is what I've learned over kind of my time here at McGill. And so the work that I do is about a slightly different type of transit than those that have been discussed. I look at asteroids from within our own kind of Milky Way, but transiting in front of stars from very far away. And this allows us to learn more about both the asteroid and the star itself. So similar to all these other kind of transits that you've seen, we have this kind of object, this body, this is not to scale whatsoever, passing in front of the star there, and you have this little drop down there, this kind of characteristic eclipse. And so for the phenomena that I'm looking at, we really want these things to be kind of, you need a camera that's capable of capturing those kind of bottom and top lines there. And that happens over the course of milliseconds. So here's a video of one of them actually happening. And sometimes this happens with extremely bright stars, and these are noted by people on the ground. You can see them, but in this case, you can see just down in the middle, star completely disappears there during that kind of transit, and then it pops back up. And so for really bright stars, these are, if you ever hear of an occultation happening to something like Betelgeuse, you could see that by eye. But in this case, you need kind of quite a powerful telescope. And don't mind those two edges. That's actually from a ring around the asteroid that was transiting. And so to do my work, I actually use this telescope here. This is the Very Energetic Radiation Imaging Telescope. It's a telescope that we basically turned into an occultation finder that used to be for detecting gamma rays coming from some of the most energetic objects in the kind of universe, and we still use it for that, but we also use it to try and find these kind of narrow millisecond edges of the eclipse that we can use to study the stars and the asteroids themselves. And so you can see each one of these mirrors. You'll see a little guy who's actually controlling the drone that pops in the left side of this video. They're about 12 meters from kind of in diameter, and we have 4 of them down there that simultaneously observe all these things. So like, you know, way back in the day when you have to travel for eclipses, with the occultations, you just randomly wait for the occultation path to actually fall over you the same way, because there's a lot more stars and a lot more asteroids than one moon and one occultation. But to build these observatories, that's why you need to travel. And so similar, you know, to Arthur Eddington and the early field kind of trips, you can see that's me taking those trips down to Tucson, Arizona, where this telescope is located. And I wish I could tell you that kind of with that observatory, we've just been cranking out transits and occultations, but just similar to everyone else. Sometimes you miss them. So this is the same plot you're seeing. And what you want to look for right in that middle is that characteristic dip. And if you don't see it, neither did I. And so this one was because the prediction just wasn't accurate enough of the asteroid's transit to actually predict where it would find. This one actually ended up going over New Mexico and not Arizona. You can also get one like this, where somebody misread the time and ended up observing it 3 minutes early. So you don't see the occultation there. You can have this one where a large cloud kind of took over your occultation, but maybe if you're patient and persistent enough over kind of just about the same period, about half the time, 3 years, you might get lucky and find a couple like this. And so that's been my work, and it's been a process of kind of trial and error. And that really is the kind of scientific process. And what I want to encourage you guys all to do when you're going to either the wonderful event at Montmégantic or this wonderful event at kind of UDM is appreciate that as you're looking at this eclipse, you're participating in this kind of long chain of people who are incredibly interested in both the kind of science behind these things and what we can use them for. And I'd encourage you just to picture yourself as a part of that kind of great scientific tradition. And so thank you.
So thank you so much to all of our speakers. We're going to move to our Q&A session. So speakers, please welcome back. And a warning, the lights are coming back on. So
Totality is ending.
So yeah, we're coming out of total darkness, so beware. Okay. All right, so now we have a few minutes. If there are any questions, but okay.
I was curious about something with this would probably only apply with regard to our moon and the Earth, because otherwise too many variables. Is there equivalent of something like the tropical Cancer and Capricorn, where you simply won't get an eclipse? Like some of the paths seem quite eccentric, but for instance, are there places near the poles where it just can't happen?
From what I know, no. In fact, I've heard and I've seen images of eclipses taken in Antarctica and in the Arctic, and of course, because the Earth has some tilt, it's easier to have eclipses at the East Pole.
Okay.
So the only thing that will prevent eclipses from total eclipses from happening on the Earth is that the moon is receding from the Earth at a very, very slow rate. So in about 600 million years, they will be more scarce, and in about 1 billion years from now, we will only have partial or annular eclipses. So enjoy them while we can.
You just ruined my next 1 billion years.
It's a slow process. Don't quote me on this. I know this has been recorded, but I think it's about the length of your thumb, the first digit of your thumb per year or something.
Yeah,
like
3.5 years. Yeah.
Yes, I have a question for Dr. White. So you talk about how we can detect exoplanets, and in the same way, is that the way to detect also rogue exoplanets? Or is it
So
more-
when you say rogue exoplanet, you're talking about planets that they're beyond our solar system, but they're not attached to a star. They're kind of just whizzing through space. Yeah. No, although I think you'd have to be exceptionally lucky. And remember that there's also a bias in the types of planets we find, because some are easier to find than others, right? Imagine you have like a Jupiter-sized planet, it's really big, so it blocks a lot of light. Having it orbit close to its host star means it's easier to see. So if you're talking about sound rogue planet passing randomly through a solar system, I mean, it's very unlikely. Now, in the search for exoplanets, I believe we're focused more on like these micro-lensing kind of approaches, those methods. But it is we suspect that they exist, right? That's in the planet formation process. Something happens where they can get ejected from a solar system, a planetary system, I should say. And so they should exist, and we're currently searching for them, but not predominantly using something like that.
The question is from Matthew. What do you learn from observing the eclipse from asteroid, because they don't have any atmosphere, so it's not as interesting as exoplanets? What do you learn from the transit?
So there's quite a few things that you can learn from these transits, and actually it depends on kind of which group is doing it. So one of the interesting things about these things that I didn't get a chance to talk about is there's actually a network of people, amateur people with kind of equipment that's only about $1,000 or less, who can set up these telescopes and just time the duration of how long that thing lasts. And from that, you start to learn about the shape of the actual asteroid itself. And so you're not learning about the atmosphere, but for example, that one that I showed you that had the two kind of dips around there, you found an actual asteroid had a ring around it. And learning more about asteroids kind of tells us not about kind of exoplanets as they are today, but we start to learn more about kind of the structure and what makes up a solar system. And that will tell us kind of about how planets evolve and how planets begin to form kind of things like the Earth. In terms of what I do is I look just at the edges, and from that I actually study the diffraction. So this is a pattern that's caused by light at the edges of this thing. It's kind of like a little bump and a little wiggle, and the little millisecond wiggle is actually telling me about how big the star itself is. And so what you begin to study is not the asteroid, but what is it's actually passing in front of, and learning more about kind of the shapes and sizes of stars with direct measurements, not just kind of inferring things, allows you to test a lot of these kind of simple equations that you would learn about. And we just haven't done that with the same number of stars as we actually, I think, could have exoplanets that we found.
What you said makes you what makes a solution do it, right? As a man, even that it's not like, well, it's not what it matter that is around a star, because you can have rogue exoplanets. So like, what is it that is planet that we doesn't have right now?
So we have some within our own solar system. You may recall there was one planet that was denoted. And older generations probably are more upset about that than younger generations. I myself did not have much attachment to Pluto being a planet, but But, we have to have conventions, like some rule for what constitutes a planet, what constitutes a dwarf planet, etc. We have all, we have classifications, even if it might have hurt those feelings. And we had set some rules about what made a planet early on. And it was a big box and we started lumping, but as our technology got better and we could explore the solar system a lot better, we started to find more things that were kind of intermediate, kind of in size, and then all of a sudden it became like, are we just gonna make everything a planet? So we started establishing rules. And so there are things like, for example, that it needs to be massive enough that gravity can kind of crush it into a spherical shape. It needs to be the dominant thing at its orbital radius. So it needs to clear its orbital path. So there can't be something comparable size orbiting also kind of nearby. And so we have these rules for it. In the case of exoplanets, we would assume that those rules would still apply to other planetary systems. And we do see them in a range of sizes, but a lot of what we've been finding is pretty big because especially with this method, because it's simply easier to see things blocking light. But yeah. I'll just also add, we've also found some exoplanets, we got a better idea of their atmospheres and they appear to have either no atmosphere, very thin atmosphere, very thick atmospheres. So everything, it is on a spectrum.
So actually about when you find out what type of atmosphere or planet you're looking at or a star, I know that these were sort of the result that you're getting in this experiment, and what are the factors that I'm 10% sure, I don't know, right? Or what are the few factors that make you even more sure that what we're looking at is actually like that?
Right. Are we absolutely sure? This is a great question. Probably should emphasize this. Everything, is qualified. We see observations of these sacred, it's not quite dark bands, it's dips in the light we receive at different colors. But it's kind of the same thing. We see empty or gaps in the light. And we know that those gaps are associated with things happening with the molecules, specific molecules will make certain imprints. And so if we see that, some pattern, we can use computer algorithms to kind of look at, if this atmosphere had carbon and carbon dioxide and oxygen and all this, what kind of imprint would it make on the light from that star and compare that to what we do see. And then we have statistics that tell us how confident we can be in that assessment. But certainly there are always other things that can, impact the light that we receive from that star. And so I would say that we do our best. But obviously, this is why we follow up. This is why as we get better technology, we go back and we re-look at the systems that we found. How do they look now? Do we still see those same things? Can we still be confident? I mean, that's the scientific process. Like you said, we're testing, we're constantly testing. Yeah.
And just maybe as a follow-up, there's Olivier, who's a student at the University of Montreal, and she and her team published results about one exoplanet that's revolving around a red dwarf. So it's the TRAPPIST-1 system. Maybe you've heard about it. There's 7 Earth-like planets, some in the habitable zone, and the spectrum that he got with the NIRIS instrument on James Webb is very, very hard to interpret. And one of the reasons, one of the main problems is that there are sunspots. There's activity on the surface of the sun, which will imprint false spectrum features, if you want. So how sure can we be? Well, in the case of red dwarf, not that much.
Yeah, but there's also cases where, you may have seen it in the news. We've detected an exoplanet that has iron rain, or glass raining sideways, or all kinds of intense weather. And sometimes we follow up with other observations, and like you just said, we learn a bit better. How can we be sure of this data? And we can say, well, we don't feel as confident that there's iron rain, or we can explain what we see with something other than iron rain, for example, or in the case of the TRAPPIST work, sunspots.
There's also complementary methods, right? So we don't just trust the eclipses and then say we're done, right? There's some systems that we can directly image, so you can actually see the light from reflected off of the exoplanet. You can see some systems where the star itself, you can detect the motion of the star kind of wiggling back and forth by the presence of the gravity of the exoplanet. And so we don't just try, well, not in this case, for very, very large systems that are kind of transitional between stars and brown dwarf systems. And so we use a kind of medley of different methods that all agree with each other. And so you can kind of look at these things from different angles, not for every system.
So I assume you know with like a high degree of precision that these eclipses in like a century or 2 centuries are going to happen because we have like really good models or something, and there's a computer somewhere doing it. How do these guys in the early 20th century or even earlier predict the path of eclipses? And what were they using? And I guess if you know, how early were we able to predict with that degree of precision where an eclipse would occur and when?
Well, so kind of one of these early records of 2 Chinese astronomers, they were actually killed because they predicted it incorrectly. So it was a more dangerous business back then. And then not every culture has been able to predict it correctly, but oftentimes you don't actually need a full model of the solar system to be entirely correct in order to have some accuracy in your predictions, right? So for a while, we had this idea that, the sun was going around the Earth, but that still allows you to predict the kind of day that it's still going to be 24 hours till the next day. And so you can use kind of just some of these kind of timing arguments and documentation in order to predict these things, but they weren't entirely very accurate. By the time we get to the 19th century, things were kind of already underway in understanding the geometry of our solar system to a much higher degree of precision. A lot of really famous transits had already happened. They've been measuring Venus transits, which have been really important for discovering some of these key features about like the distance and geometry of our solar system.
And what's interesting is that, like you said, you don't even need to know exactly how the solar system works to know that eclipses are going to occur. And I know that like 3,000 years ago, there was a general idea that eclipses were happening at specific intervals. So the Babylonians, for example, knew that every 54 years there would be an eclipse happening about the same region. And in fact, this is 54 years is 3 Saros. So a Saros is a cycle where a similar eclipse will happen. So, for example, we have an eclipse in 2024, and 18 years after that, there will be a very similar eclipse, but it will just be shifted, I think, towards the east. So by that, there was a way to know that there would be eclipses. But I guess that as soon as, like, for example, Kepler's equation were well known, we could predict with a high degree of precision. In fact, the eclipse from 1919 was known to be one of the longest eclipses to occur for at least a century. And it was known that it happened in front of a cluster of stars. So this is why there was a lot of emphasis on this expedition.
This would be a question for Dr. White. I'm thinking that some of the outer planets in our solar system have extremely slow period, several dozen to, I think, 100+ years for full orbit. Is that a limitation when detecting exoplanets? Because essentially there may not be a transit,
Yes.
before we actually get there.
Exactly. I mean, we've only been, monitoring the stars for evidence of orbiting planets, like I said, for like fewer years than it would take to, for example, like Neptune to go around or Saturn or something like that, right? Like, so yes, it is a limitation, and it's also part of our bias. Remember, so for a long time, we looked at our own solar system and thought to ourselves, okay, whatever our solar system looks like must be just replicated, right? And the more that we, with the discovery of exoplanets, what we've been finding is a lot of evidence that A lot of systems don't look like ours, right? And so it's been enormously helpful in understanding what do planetary systems look like in our galaxy and in the universe. However, there is this limitation, right? So if we look at the types of systems we found them at these distances, this one in the habitable zone, this one not in the habitable zone, etc. There is a limitation in understanding these sort of long period planets and what are the sort of sizes of solar systems and things like that. And it's because we simply don't get a second dip, right? Even if we saw it. So yeah, so it is obvious.
About the eclipses, I was wondering, on the long term, is the fact that the moon is receding from the earth affecting how much light we see in the rain during the eclipse?
Yeah, well, just like I said a bit earlier, on the very, very long term, yes, it will, because there will be a point where the moon will be too far away. But on like in your lifetime, it's really about where is the moon on its orbit? Is it at the closest point or the farthest point? So this has much more influence in your lifetime on what type of eclipse and how much of the moon, how much of the sun will be covered, and the duration of the totality, of course, because there's like a few factors that will increase the time of totality. If you're closer to the equator, if the moon is at its perigee, if the Earth is at its farthest point from the sun will be smaller. So all that can have an effect. And when you have all the right conditions, then you can have a totality of about 7.5 minutes. This is the longest theoretical totality that you can have, unless you have a Concorde, like some scientists did in 73, when they flew in the path of totality at Mach 1.6, I think, and they were in the totality for 103 minutes. There's a very good documentary on YouTube that you can find about that. Very interesting.
Okay, let's do two more. Go ahead.
Like on the pie chart that you showed, like what types of eclipses there are, like partial, annular, and total. Also saw hybrid.
Yes.
Like 4.8%. What is that?
It's an hybrid eclipse is an eclipse that happens when we are just on the edge of the moon being large enough in our field of view to cover the sun. So, of course, because of the Earth's curvature, the distance that the shadow travels will not be the same. So hybrid eclipses can start as an annular eclipse and then transition to a total solar eclipse or both. So in fact, this spring there was an eclipse in Australia, Indonesia, and it was such an eclipse.
Thank you.
Or eclipses, or
Yeah, like ones are in the satellites.
I don't think you would see satellites during totality. The sky gets darker, but not as dark as it is during the night. So you can see a few stars, you can see planets, but satellites, I don't think so. So it's really much more on the like astronomical observations at night, radio astronomy, which are greatly affected by satellite constellations. So I personally, I don't do research, but I do like every night during the summer, I point telescopes with people at the Astrolab and show them cool stuff in the sky. And like when I started 20 years ago, maybe once or twice during the summer, I would see a satellite pass in the field of view of one of our telescopes. Now it's many times a night. So it's already spoiling the sky just. Yeah, clouds are your main concern, not satellites.
But I would also add that it's not just, so I agree, some observations I took with the network of telescopes just a few months ago had satellite trails going through them, and it was pretty frustrating, a beautiful image of the galaxy, the satellite trail. One thing I will just add is that the predominance of satellites, ones that we can actually see with our eyes, it's also a satellite-filled sky will change our own cultural connection with the sky. When we look up at the sky, we see stars, we see all these things. We grow up seeing the Big Dipper, for example. Like a night sky full of stars will also change our connection with it. If you imagine like a corporate constellation of running through the night sky, right? So satellites do run the risk of having a huge impact on humanity's connection to our night sky as well. So even if they don't impact the eclipses, I mean, let's all keep an eye on Starlink.
Yeah, so you're right to be concerned about satellite constellations. I think it's a discussion that, as an entire culture, we haven't really had, and it's just been growing and growing in prominence. There's now, we were looking at this Chinese satellite that was just recently launched that, is the size of like a swimming pool. The Starlings themselves are each about the size of a Ford F-150 with a giant sail on it. And these things do impact not only astronomy, but like Heidi was saying, kind of our cultural connection to the sky. And they also kind of pose a risk to themselves. These satellites, some of the best observations and a lot of these images that you were seeing from Cassini, and sometimes you'll see a ton of Hubble images in these, are only possible because of this network of satellites that we put up in space for astronomy. So having satellites is extremely important, but if these satellites start to crash into one another and form these kind of large clouds of debris, it makes it difficult not only to do science, but to do anything. So, yeah.
Would black holes have an effect on the
So black holes are really interesting objects when it comes to a lot of things that we've talked about today. You can see occasionally black holes in orbit around other systems. You could treat them like kind of the same way that we used to find in sometimes exoplanets in these kind of systems where they're orbiting around other systems is the only way that you can find a lot of these things. When it comes to the impact on kind of eclipses within our own solar system, we don't know of any black holes, which makes it really easy to not be obstructed with regards to these eclipses. But it is that they are tremendously interesting as well for like I was talking about this micro lensing stuff, and gravitational lensing was what I talked about, this bending of light around sources, and that's one way that we try and find black holes that are all similar way that you find exoplanets. So they're really interesting connections with the kind of things that we talk about. Anything that doesn't emit light is similar in some ways. But yeah.
All right. If anyone has any other questions, we'll stick around for a few minutes, but let's thank our speakers one more time. So I just have a few quick announcements. So one is that the McGill Physics Hackathon is happening next month, and registration is now open. This is a weekend-long coding challenge. So if anyone is interested, please check out the McGill Physics Hackathon on the McGill Physics website. And in terms of our upcoming events, we have this partial eclipse watch party that we're going to with UDM. So TSI will be there as well. So come and hang out with us on October 14th. And also we have 2 public talks coming up. The best way to keep in touch with us and up to date with all of our events is to follow us on social media. And these are our links. So with that, our 2 winners of the TSI mug are Clotilde and Sobia. So if the 2 of you are here, please come see me, and thank you again. And we hope to see you next month.
Really good photo.